Hello, this is the section 3.7 lesson. In chapter 2 we talked about defining a new random variable in terms of an old random variable. That new random variable is what we call a function of the old random variable. And then we talked about how to calculate the expected value of this new random variable. Well, in section 3.7 we're going to do essentially the same thing, except that this new random variable we're going to define is going to be in terms of two old random variables. That new random variable is called a function of those two random variables. And so we're going to list some properties that deal with any type of random variables or functions of any types of random variables. And we're going to also list some properties that apply specifically to independent random variables. So we're going to start off by defining the mean or expected value of a function of two random variables. So here our two random variables are denoted x and y, and this function is called u of xy. So the expected value of that function is, we're going to take the function times the joint PDF, and then we're going to integrate over all possible values of x and y. This definition is very similar to our earlier definition of the expected value of a function of a single random variable, except that now we're dealing with a joint PDF rather than just a marginal PDF. So to illustrate this idea, suppose the joint PDF of two random variables x and y is given by this. Now we saw this joint PDF in the previous section. And suppose we want to calculate the expected value of this new random variable defined in this way. So our new random variable is equal to x times y squared plus 3x plus 2y. And so by definition, we're going to take that function times the joint PDF and add and integrate over all values of x and y. Well, in this case, our PDF is 1/2 only for x between 0 and 1 and y between 0 and 2. So we only need to integrate over this range of x and y, and then we integrate that using standard calculus 3 techniques, and there's our expected value. Now next we're going to list a couple of properties of this idea of expected value of a function of two random variables. First theorem has two parts to it. The first part says that for any discrete or continuous random variables, the expected value of the sum is equal to the sum of the expected values. And then the second part says that if x and y are independent, then the expected value of the product is equal to the product of the expected values. Now this second part only applies to independent random variables. The first part applies to any type of random variables. Independence is not needed. The second theorem also deals with just independent random variables. It says that the variance of x plus y is equal to the variance of x plus the variance of y. And so the variance of the sum is equal to the sum of the variances, if they're independent. So to illustrate this first theorem, let's look at a couple of examples here. So let's let x and y denote the weights of two randomly selected people. And let's suppose that the expected value of each of those weights is 220 pounds. And then we might ask, what's the question, or what's the expected value of their total weight? So if we combine them, if we somehow like put them together in a car or something like that, what's their expected total weight? Well, in terms of x and y, we want to know the expected value of x plus y. And according to our theorem, that's the expected value of x plus the expected value of y, which we're told are 220 each. We add those together, get 440. That's it. The expected value of the sum is the sum of the expected values. Another example, suppose we take two sticks and we cut them to the same random length. And then we take two other sticks and cut them to the same random length. Now those random lengths may not be the same for the first pair as the second pair. And then let's suppose that we form a rectangle from the four sticks. And so let's let x denote the length of the first pair and y denote the length of the second pair. So what we've done here is formed a rectangle where like the height is x and the width is y, or vice versa. And so we might ask, so let's suppose that the expected value of x is 6 and the expected value of y is 8. And further suppose that x and y are independent. Now, we might ask the question, what's the expected value of the area of that rectangle? Well, the area of the rectangle in terms of x and y is just x times y. So by our theorem, and because things are independent, that's equal to the expected, or the product of the expected values, which is 6 times 8, which is 48. So that's all there is to calculating the expected value of the product of two independent random variables. Our next result is kind of a complicated looking theorem, but it's very useful and actually not that hard to apply. It says that if x is normally distributed with mean mu sub x and variance sigma squared x, and y is normally distributed with mean mu y and variance sigma squared y, and x and y are independent, and a and b are constants, then this new random variable w, defined to be a times x plus b times y, is normally distributed with this mean and this variance. So you see, to calculate the mean of this new random variable, we simply multiply the means of x and y by their respective coefficients and add them together. And then to calculate the variance of this new random variable, we square the respective coefficients, multiply them by the respective variances, and add them together. So our last example is going to be a simple application of this previous theorem. And so let's consider these two random variables x and y that denote the weights of the people from this previous example. And let's suppose that those random variables are independent and that they're both normally distributed with a mean of 220 and a variance of 29 squared. Now let's define this random variable w to denote the total weight of those two people. And in terms of x and y, that's just x plus y. So we have here is w is 1x plus 1y. And so by our previous theorem, w is normally distributed with a mean of 1 times 200 plus 1 times 200, and then a variance of 1 squared times 29 squared plus 1 squared times 29 squared. And if we do all that arithmetic, we get a mean of 440 and a variance of 1,682. So then if we wanted to, for instance, calculate the probability that their total weight was greater than 500, well, w has a normal distribution with this mean and variance. And so we can convert this number over to z-score, subtract the mean, divide it by its standard deviation. We get this number. And so the probability that z is greater than that number is equal to this using table C1. And so there we go, the simple application of our last theorem.